restart the recording. Okay, or the floor is yours.
Thank you so much, Sivan. Yeah, maybe just a quick clarification because I've been asked about this. It's not that I get tired of places too early. It was basically one long postdoc with the same advisor. Only the moment I got to Stanford, my advisor took a sabbatical year, so I joined him at Facebook AI, which was wonderful. But then we went back to Stanford. It's the same postdoc. So as Sivan said, I'm Or, and without further ado, let's jump right into learning on point clouds for 3D scene understanding. I think it's maybe a good idea to start by, telling you a little bit, maybe setting the same stage for everyone or getting everyone on the same page about what is 3D scene understanding, and then why I think, or what I think makes learning on point clouds so exciting. And hopefully, once you're convinced, we can jump into the core of the talk. I have a lot of content here, but I don't want to stress too much. So feel free to stop me for questions. We don't have to go through all the slides. So what is 3D scene understanding? Let's consider the general setting where we're given some 3D content as input. And the ask is to give some useful semantic and geometric signal as output. And by useful, I think someone's mic is open. Maybe if you can mute yourself, it'll be easier. By useful, I mean usually it's actionable. So we want some output that we could use for some later downstream task. Let's make things a little bit more concrete. So let's consider the following input setting. So now I'm making the input 3D. Earlier I said it could be 3D content. Now I'm making this concrete. I have an RGBD camera. I may or may not use the RGB channel. That's here just for us to see better what's going on, but you can ignore that for now. I'm mostly concerned with the depth here, the depth information. And let's go through a bunch of examples of what could be considered as proper, quote unquote, downstream tasks that are semantic understanding. So maybe the first one that we're kind of very intuitive, but also probably the most general is scene classification. So I want to be able to declare that this scene here is a home office. Why is this useful? I said this needs to be actionable. So imagine you're an architect and you need some inspiration for designing a house and you want to search Google. Maybe Google 5 years from now is mostly or has a lot of 3D content in it because we all have scanners. Then you want to be able to retrieve these examples, right? And get some inspiration, maybe even take some measures, things like that. It could be very useful to just use as a search query. A room layout starts to be a little bit more geometric, right? Why is this useful? And by room layout, I mean, at least I want to detect the floor and the walls. Well, one useful application is, I don't know if you ever played Pokemon Go, but it'll be nice if the Pokemons are on the floor and not floating in space. I'm sure there are some more that are examples that are better important for advancing humanity, but this is a very intuitive one. If we like semantic segmentation is a very useful task. It's a much stricter, much more strict ask here because we're basically telling that the output should be dense. We want for every pixel in the input image or every point in this point cloud, we want to assign some semantic label to it. And again, this is very, very helpful for example, VR applications, if you want to replace objects or extract them or any of those things. But today in my talk, I'll focus mostly about one of the probably most explored and most useful tasks. And I'll tell you more later about why I like this task in particular, but I'm talking about object detection. Just in 2 words, this means that we want to be able to find all the interesting objects in the room, put some box around them and tell what is the orientation of the box and also what is the semantic class of the content inside that box. Okay, let's say that we are convinced that it's interesting to solve scene understanding. Now we have the following issue. We want to do this from 3D data. So recently, I don't have to tell anyone, it's not news that we have very strong tools of deep learning, and it may make a good idea to try and apply them to 3D data. It turns out it's not very obvious how to do that, right? Because if for images we have pretty mature technologies now in the form of convolutional neural networks, 3D data or 3D content can come in many forms of representations, and all of them are useful. I'm not arguing by any means that one of them should dominate and we should keep it and get rid of the others. All of them have their own properties and are useful in many applications. I don't want to spend too much time on this, but for example, meshes are widely used in graphics. We probably won't replace them in the near future, but it means that we also have to design neural network architectures that can consume each of these representations and spit out some interesting results. So it's not trivial to do. And in today's talk, I'll focus on point clouds. So let's try this. I'll try to convince you why I think point clouds are interesting. Well, first thing that's interesting about point clouds is that these are the raw outputs of some sensors. So much like pixels could be considered as the raw output of our image sensor, and that's why it makes sense to develop convolutional neural networks to process them. Now, point clouds become the immediate raw output of sensors. It could be lidars mounted on top of cars that I see drive by my house in the Bay Area every day, or it could be the new iPhone 12 that's already equipped with a lidar and lets us do all kinds of exciting stuff. So, given that this is just the raw output, it's already convincing enough that we need to develop technologies to process this. Now, what's challenging about about point clouds is that unlike 2D images, which are given in some very structured way, right? We have converged as a community that the representation of images is a 2D grid. Then in 3D point clouds, that's not the case. The points are unordered. If you want to think about this in terms, without going into terminology, we'll go into that later. I could say that if I shuffle those points around in order, you'd still want to be able to say that this guy here is a horse. And they're also irregular. So we don't have this nice array structure that we could assign an address for every point, but they could be in a continuous space. And also, if we sample the same object twice, we might get actually a different sampling of the underlying surface. So this makes the problem challenging. And unlike 2D, this is much less mature. I would say that in many ways, this field is in its infancy. But there have been some very exciting works out there, starting, I guess, 3 years ago now with Pointnet and Pointnet++. And I'm listing just a handful, but really there are many, many works. And if we have time, hopefully I can also tell you about some exciting work that we've done on this recently. But we're starting to see some technologies developed for processing this. And in my talk, I'll be using them. I won't explain them in details, but just take into account that this is a very exciting topic and there's lots to do here. So hopefully now you're convinced that 3D scene understanding is useful and that learning on point cloud could be challenging. And today I want to show you what I've done with this for object detection and in 3D scenes. And later on, I want to spend my view on where should we go with these technologies and how do we progress this into the future, where we might not have the luxury of getting full supervision for all our tasks. Okay, so the first work is called deep half voting. Don't worry if half voting doesn't ring a bell. It's probably been a while since you heard about this. So I'll give a proper kind of a 1-minute reminder of what that is. And this is joint work with some great colleagues like Charles, who's now at Google's Waymo, Qingdei and Kai-Ming from Facebook AI, and my postdoc advisor, Leo Kibas. Okay, so I want to tell you what I think is interesting about 3D object detection. First of all, I've already told you what that is, right? We're given a scene full of objects, and we want to estimate the oriented bounding box of the interesting objects, and also be able to say the semantic class of the content of each of these boxes. The reason I think this is really nice is because, to me, this is the most concise way to explain a scene. Right, and by concise, I mean, instead of keeping around 2 million points, imagine, we're replacing this with, let's say, 5 or 6 or 7 boxes. This is a very low-dimensional representation of the underlying scene. Of course, we're throwing away lots of information and detailed geometry, but we're keeping around, in some sense, very important cues. Here's an example. I could already send an agent to navigate in a scene without bumping into any of the objects. So as long as that agent knows about the bounding boxes, right? So we're seeing some very nice, I'd say some very elegant way to say, take my robot, go to the refrigerator, right? All it needs to know is that there's a bounding box tagged refrigerator. So it already allows us a bunch of downstream tasks while being very low dimensional. So this is why I really like this task, and I think this is why the field is so excited about this task, both in 2D and 3D. But when we started the project, what we found is that in many ways, previous works have tried to tackle the problem of 3D object detection the way we tackle the problem of 2D object detection. And I'll give you kind of a brief overview of what's been done before that. So one, yeah, and you'll get what I'm saying when I'm saying this is 2D. It's either explicitly 2D or it's 2D in nature. So the first line of work is trying to mimic 2D object detection, just lifting it by one more dimension, right? Instead of XY, we now have XY and Z. And the way, a very popular method to do 2D object detection I would say the dominating method to do 2D object detection is to do object proposals. And just to give you like the highlight, this is basically saying that we're traversing across the 2D array, and we're giving proposals of what could be a region that contains an object. And then we're giving that region into another network that tells us whether the object exists and maybe refine the box a little bit. This can work in 2D because there aren't that many pixels. So we can actually do this. But now if we try to lift this to 3D, we start to suffer from the curse of dimensionality. And we actually, it becomes too computationally intensive, and we can't afford doing the same method in 3D. And I can show you some numbers about how this affects time and computational complexity. So this is not the way to go. And you could argue, but wait, there aren't points everywhere. You don't have to actually search the entire 3D space. So keep that question in mind. We'll go back to that and I'll explain why you actually do have to do that. Another popular line of work is the bird's eye view detector. So in this case, as you can imagine, we take the 3D scene, let's say sampled from a LiDAR on a car, and we somehow project all the points into the plane. We don't have to just directly project them. We can first process something along the height axis, but in many ways, we're losing resolution along the height axis. And this is a very popular method for 3D object detection in outdoor scenes. And I think the reason is that it's maybe okay to lose some resolution in driving scenarios. For example, it's very rare to see a car mounted on top of another car, right? This is probably not something that we're expected to handle. But in indoor scenes, this happens all the time, right? Just if I'm looking around me now, I can already see that, I'm sitting on a chair that's already underneath a desk, and on top of that, there's a laptop and maybe some lamp. So you see that we can't afford losing resolution. We need a good resolution along the height axis, probably as good as we need along the X and Y axis. And the third line of work is a frustum-based detector. And this work basically says, okay, it's too expensive to search entire 3D. So let's first detect objects in 2D. Once we found them in 2D, and this also assumes an RGB input, I should probably mention that. If we detect the object in 2D, we can just limit the search of where it is along the ray to this frustum. But as you can understand from the way I described it, this is a sequential process. So if we couldn't detect the object in 2D from the image, there's no way we can retrieve it from 3D because we will just not create a frustum search space there. So this is why basically I'm calling all prior methods 2D, either properly 2D or 2D in nature. But in this work, we wanted to go back to first principles and really tackle the problem we have here, which is a 3D point cloud, and ask what is the way to go about detecting objects from the point clouds directly. So I want to share this interesting insight. Look at the image here. We're not using the image in this work, by the way. We're not using any color information, but for us as people, it's just easier to appreciate what's going on. Here, this is the same scene, only represented as this point cloud. I tried to put some diagram of this table here on the side and see what's going on here. Remember, I told you like the popular way to do object detection is to do object proposal. And what happens is that a good object proposal needs to come from the center of the object. This way we can get the good content of something that that occupies the entire object. But the problem is that object centroids could actually lie in empty space, because the input point cloud is what the sensor is sampling, and the sensor is sampling from existing surfaces. So it means that actually the real object centroid could lie pretty far away from the object surface, and we won't have any points there. Or if we use terminology, we don't have any support there. The point cloud networks, they work on the points. This is an interesting bit about working on 3D point clouds. Unlike 2D, where you can think of the 2D array as your canvas and the pixel values as the function defined on top of that domain, in 3D, the points are both the domain and the function. So here we don't have support if we want to do something in empty space. So what could we do? Well, we could create a support, right? And how do we create a support that lies near the object center? We could literally ask, or not literally ask, we could conceptually ask the surface points where they think the centroid of the object lies. And this is exactly how this idea of our project was born. We were saying, we have the surface points here, but we need support near the object centroid. So we're going to vote. We're going to let every point in the actual scene vote for where it thinks the center of the object it belongs to lies. This way, we get the points talk to each other because they're now in spatial proximity, and together they can decide on an improved proposal. Okay, here's the gist of it, and let's kind of delve into the details. Maybe first a quick reminder, or I have to first hedge and say this is by no means our idea. Voting is a beautiful idea that was kind of born not even in this 40-year-old paper that I'm citing here. There was a prior work to that was half transform, like a beautiful method that I think initially invented to detect straight lines in gas chambers, but some adaptations of this from just detecting geometric primitives to detecting objects was done in this very famous, I should say, like a seminal work about generalized half voting. I'll take you through it really quickly. I remember like really enjoying learning about this from Shai Avidan. Now it's my turn to tell you about this a little bit. Basically, this is the setting. So let's say we're interested in detecting cows, okay? And I give you some collection of cropped images of cows. Cropped, I mean, you already know the bounding box around the cow. And what we're going to do is the following thing. We're going to run a key point detector. Doesn't really matter what that means now, but just imagine that what it finds is some points that the algorithm thinks are interesting. And usually those points are not near the object center, but they usually are where interesting texture happens, which is in the boundary mostly. So once we found the interesting key point, like maybe here on the, near the tail here, then we're going to open a patch around it. We're going to look at what we have in that patch. And we're not going to just keep that patch. We're going to also keep the displacement vector that's going from the centroid of the patch to the centroid of the objects. We have that at train time. We can do that for all our training set. Now, when it's time to do inference, when we're given like a real scene, like with those two cows here in the field, and we want to do cow detection, we start the same way. We start by running a key point detector. Here we found a similar key point. We don't know that yet. We're just opening a patch around it. And now we're seeing, oh, wait, this patch actually looks a lot like this one. Why don't we copy this displacement vector from here to here? And that's exactly what we're doing. We're going to keep doing that for many different key points. And before I move forward, I want to pause for a second and just have your attention paid to what we have here. You see the underlying image here is actually, I'm not interested in the image anymore, right? The image was the 2D array that I've mentioned a bunch of times by now. But what I'm actually interested in is the sparse set of key points, the yellow key points here. And this is already much more similar to the 3D case we're interested in, right? So you can already appreciate why this jumped to mind very quickly when we started working on this. So I'm going to keep going through the key points, finding their matches in the training set and copying the displacement vector. And as you can see, the agreement is translated to accumulating nearby displacement points, right? Or votes, as these are named. Now, this is very strong because, oftentimes we'll have some outliers, right? We'll have some patch that maybe reminds us of some part of the cow, but is actually not. And that's okay. So as long as these don't accumulate, right? So we can accumulate signal. It helps us get a better signal to noise ratio, if you will. And at this point, we can decide, okay, maybe we tessellate the image into some cells, and we count how many votes we have in each cell. And if we pass some threshold, then we can declare, great, we found a cow. We're not done yet. There's still one more task to do. If you remember, the object detection task is not just about finding the object, but it's also about retrieving the bounding box. How do we retrieve the bounding box? It's easy. Here, we can go back. Oh no, I'm losing battery on my headphones. Can you still hear me? Can you still hear me well?
Yes. Yes, we can hear you.
Okay, let me know if you lose me, because I'm getting some low battery on my headphones. So at this point, we're not done. We want to retrieve the bounding box. And the way we do that is by tracing back, because we know the points that originated the votes. We can trace those back and then just put a bounding box around all of them. And remember, that point is going to actually be crucial. Okay, so let's kind of, there's one canonical example that is often shared, but I think we can skip this. You know what, let me say a word about this. There's an interesting aspect here of context. In this, I'm gonna mention some differences between this work and our work, obviously. And the one thing to remember about this work, this is pre-deep learning times, is that context is just that patch that we cropped around the key point. So for example, if we found a key point in the center of the wheel, there's no way we can tell whether it's the front or the back wheel, right? Because that's all the context we have. So a nice hack around this is to assign multiple votes. So we can say, okay, I'm either the front or the back wheel, I'm gonna vote twice. And again, very much like the case of getting rid of outliers, here we have, we know that the center of the car will accumulate while the other votes will not. So we have, again, this nice signal to noise ratio thing. Okay, so what are the good things about this? This is very suitable for sparse data. I mentioned earlier that I don't care about the image. Very early in the process, I only care about the detected key points. So this is quite similar to our case. And this has this nice baked in property of long range and non-uniform context aggregation. And you'll get a better understanding of what that means in a second. But of course, it's not end-to-end optimizable. We're talking about like some techniques that are that don't use the modern technology that now we have. So it's time to tell you what we've done and how we adapted this to a deep learning framework. And this is called the deep half voting. So again, we're starting with an input point cloud. This is a 3D point cloud in this case, not 2D anymore. We're using as a backbone one of those point cloud networks that I mentioned in the earlier slides. And I also told you that I didn't go into the details. So you, at this point, don't, you're not supposed to exactly know the details of what's going on here, but this is not my focus. So I'm going to skip that and assume that we're just using one of the existing off-the-shelf backbone neural networks to process point clouds. What is important is the output. The output we get from those networks is every point is now enriched with a high dimensional feature. And the way this feature was created was by aggregating the neighboring points. So this is the context. And using that context, we now have every point has its own location, but it also has a high dimensional feature vector that hopefully knows something about its local geometry and shape. Now, using those enriched points, we can, and I'm calling them seed points because at this point, we don't really need to keep around all the input points. After we've accumulated context, we can actually get rid of a lot of them and just keep a subset. So this is what we do. We keep a subset of the points enriched with features. And now here comes the place where we ask the points, quote unquote. We go to each point and we say, using your location and your feature vector, please tell us what is the displacement from your location to where you believe the centroid of the object you belong to lies. And this stage is actually supervised because we have the at train time, we have the bounding box. So we know the centroids of those bounding boxes. We can supervise that the votes of those points get to near the centroid. This is great because look at what it did. It created a new point cloud. This one is not point cloud in the sense that it was sampled by a sensor, but rather it's a virtual point cloud. It was created by existing points, but it's much better structured. It's already clustered. And this means that if we now pick points at random and we open some ball around them, then we're aggregating points that come from all over the object. So we've converted very weirdly structured objects into just neighbors in we've converted maybe some feature similarity to spatial similarity. For those of you who are familiar with attention mechanisms, it's kind of a you can think of it in these terms. Now, once we have brought all the neighboring points, all the points that belong to the same object to talk to each other because they're in neighboring locations, they can together be filtered and through, again, another neural network and agree on the refined location. So this is not just the average of those points. We can actually have those points communicate to another layer, through another small network to agree on the refined centroid location, and also about all the other parameters of the bounding box: the size, the orientation, and the semantic label. This is again a very interesting difference from a very interesting difference from what I showed you earlier, because if you remember, earlier when we wanted to retrieve the box, we had to trace back the voting points, the points that voted to that location. You know what? Let's get back to that in a second. I want to first show you the network pipeline. So here on the bottom, I just pasted again the intuitive process, and here on the top, I'm just putting the neural network blocks. I'm going to run through this quickly because I don't think this is the most interesting part, and I have a lot of other stuff I want to talk about. This is the backbone network I mentioned, the Pointed++. So we started with an n/3 point cloud. This is the backbone network. Could be Pointed++. Recently, I actually replaced this with another network. It kind of worked out of the box, so it doesn't really matter. This is M smaller than N subset of key points that are not just X, Y, Z. This is the 3 here, but also has a high dimensional C channels here. And this is the voting. I just want to emphasize that the voting happens separately for each point. So using using its location and the high dimensional feature, it just needs to tell us what is the displacement to where it thinks the red points, right? The votes or the centroid of the object they belong to lie. This is we get a natural clustering because we get a natural clustering because we supervise for it, and now we can sample and group. And by this I mean we already have the clusters because we supervise for them. So if we sample a point, we get a natural grouping. And now using that grouping, so now your neighboring points are neighboring virtual points. This could come from anywhere in the object. Together, they generate a proposal. We decide to choose K clusters, these are the hyperparameters of the network. And once we've kind of declared on K bounding boxes, we run them through a non-differentiable. This is done in post-processing stage, a non-differentiable 3D non-maximal suppression. And we're left with K prime boxes depending on this, the result of this algorithm. And in terms of loss functions, what we have to manage here are a bunch of loss functions. First of all, we have the regression of the location of the vote. Then we have the objectness score, which basically tells us for every point whether it believes it's part of an object or a background. Then we have the parameters of the box, like the orientation and scales and everything, and of course the semantic class. So you see, this is a quite interesting problem. It involves both classification and regression. Okay, let me highlight a few interesting insights here. One, I think I mentioned a few times now that the votes are virtual points. The nice thing is that we already have technology to process point cloud. We're again processing point clouds here. The only difference is that this point cloud never was sampled by a sensor. It was created virtually by existing points. And the other thing is this thing I wanted to emphasize earlier. So here to detect the cows, we had to trace back the originating points. In our case, we don't have to do that. Already these points contain enough information in their features to agree together on the object and its bounding boxes. This is especially useful in 3D object detection because a lot of times the requirement is to retrieve A model proposals. And what I mean by A model, the simplest way to think about this is that imagine this cow occluded this one. And someone would ask you, please give me the bounding box of not just the tight bounding box around the half cow, the occluded one, but now I think I lost my battery. Oh, it should still work. So imagine that someone asked you to retrieve the full bounding box of even the occluded part of the cow. Then in this case, it's very hard to do because you never found a point on the boundary of that cow. It was occluded. In our case, we can easily do that, right? Because we only use the point in the center, and they could already know. For example, look at this, right? We have just the upper part of a chair, but there aren't many chairs floating in the air. right? So the network already has a very strong prior about if I'm on a chair, then most chairs are mounted on the floor. So probably the center of the object or the bounding box should touch the floor. This is a very strong prior that could be learned from data. And in our case, it has the opportunity to learn it, while if you're learning it, in the original generalized half voting, there's no way you can do that. This is why I'm highlighting this. Great. Okay, so actually, one more interesting thing, because I mentioned the attention mechanism earlier. So if you think about the way neural networks work, this is true also for 2D neural networks. Usually, the deeper you go into the network, you kind of grow your kernel uniformly, so your receptive field. You see more and more points, but in a uniform way. This is not always the best idea, right? Imagine that you actually care about some very elongated object or something like that. Then you'd want the aggregation to, as you proceed, you want to aggregate points, but in a way that could follow the structure of the underlying object. And in some sense, this is exactly what we're proposing to do here, right? We're taking some weirdly structured objects, but we're forcing them to, to shift from feature similarity to spatial similarity so that we can just process them using existing tools, and thereby creating like non-uniform aggregation of context. Cool. This is also one reason that if you remember this example of the wheels of the car here, it only had a very limited context and therefore had to vote twice. We actually have a much larger context. We also added the functionality of voting more than once, but in practice, this didn't change anything. And my guess is because we just have better context aggregation, so it's not needed. Let's look at some results. So two famous benchmarks in the task of video object detection are the SunRGBD and ScanNet. They're quite different. I'll say a few words about them. SunRGBD, as the name suggests, is RGBD, so it comes from a single view sensor. We're not using the RGB channels in this work, just the depth. And the main thing to understand here is that the type of partiality that single view create is usually self-occlusions, right? If you see an object just from one side, it has self-occlusion, so you may not see the back side of it. ScanNet is a very different benchmark. It usually contains much larger scenes that were first sampled by walking with a scanner throughout the room. So we have the full scan of the room. Of course, there are partialities from places where the camera couldn't reach, but mostly this is much more complete than SunRGBD. But it's complex in the number of objects and the scale of the scene. So it's very interesting to run the algorithm on both. Here, again, I'm showing the image just so that we can appreciate what's going on. We're not using this as input. This is our VoteNet prediction, and this is the ground truth here on the right-hand side. I kind of like this example here on the top because you could see that I have a lot of, I don't want to rant here about the annotators of the data set, but you could see an interesting example where maybe the annotator was a little bit sloppy and didn't finish annotating all the chairs in the classroom. But it's kind of cool to see that VoteNet was confident enough from its train time to predict more chairs that were even annotated by this test time example. This is another interesting case where we're able to find this nightstand next to the bed, even though like you can see how many few points there are here. So I'm pretty happy about this result. From ScanNet, first of all, you can appreciate that the scenes are much larger and complex. Actually, I want to use this benchmark to, in general, I think VoteNet did a pretty decent job here, but I do want to highlight some failure cases that are interesting, and it could be a nice segue to the second part or the follow-up work we had. Which is, look at okay, in the center of the room, everything looks pretty good. Maybe we split this elongated table to multiple smaller tables. Maybe we didn't have much of these at train time, but look at what's going on here around the border, right? Here we have very thin structured objects that were annotated. For example, curtains and windows and doors. VoteNet is just using geometry. It's very hard to distinguish a door from a wall. Yeah, here's a good example. Here at the top, there's a door. It's could be just seen as part of the wall to the network because it's just points. So this is exactly the place where we thought using more than just geometry could help. But yeah, before we move on to that, some numbers. I think the main thing to look at here is the input in all prior work was both the geometry and the color. When we started the work, we actually thought to use both, but we decided to, give a proper attention to the geometric part. So we said, let's squeeze as much as we can from geometry before moving forward. And we were kind of surprised to see that already by using just geometry, we were able to surpass all previous results. And I think this goes to say, just to circle back to how I started by telling you how all prior works are kind of 2D in nature. I think this is just evidence of that in some sense. I think just because we more properly process the geometry, we were able to squeeze more out of it without hoping that RGB will kind of come to the rescue. This is oh yeah, sorry, go ahead.
What are these numbers? What did we see in the table?
Right. Yeah, sorry. So this is the mean average precision. So we're basically think of it as like we're measuring, we're deciding like a hit or versus a miss if we get good overlap between our predicted bounding box and the one that was annotated by the annotator. And the number here is whether we consider a hit or a miss if the overlap is above 25% or 50% of the overlap. The intersection of reunion, I mean.
Okay, thanks.
Sure. Okay, so I think now's a good time to say, now that I kind of trash talked a little bit the previous method that used RGB. I'm kidding, of course. These are super useful and insightful works. Now it's time to ask, what about the image, right? Because we've seen that VoteNet misses thin structured objects, or in other cases. So it makes a lot of sense to incorporate RGB image. So in this point, we were asking exactly this. What about the image? I think this is a nice visualization that shows the same scene. Here's the image, here's the point cloud. And you can already appreciate that the signals are complementary, right? Images are high resolution and they see through, they can see blind regions. And I'll explain what I mean by that actually by using an example later on. But an interesting takeaway from this is, sometimes there are objects that are completely missed by the sensor and the images can see them. And the high resolution gives us some interesting things, not just color, right? We have texture and we can also have geometry from 2D. 3D has absolute depth and scale. This is very useful, right? In images, we don't know if an object is close and small or far and large. In 3D, we actually have the absolute depth, but it's much sparser and lacking resolutions could be also noisier. So how do we combine them? Well, this idea that basically we're very excited about the votes. And what we wanted to do is find a natural and organic way to incorporate the 2D image into our existing framework of 3D voting. And how we can do that is just by do 2D voting. And I explain how that works. So let me show you a scary diagram and walk you through it really quickly because you know most of it actually. So the bottom part here is VoteNet. This is the work I just presented. So you've seen this. This is starting from the endpoint point cloud, running it through our backbone point cloud network, keeping those seed points. And then right before we're about to take a seed point and ask that seed point to vote to where it believes the center of the object it belongs to lies, we're going to pause right there and go to this branch. This branch is a 2D detector. It starts from an image. It runs 2D detection. So we now get 2D bounding boxes around the objects. And what we're going to do, because we have a calibrated camera, we know every pixel. We already know, we know what's the correlation between every pixel here, or it's the opposite, between every point, every 3D point here and the corresponding pixel in the image. So right before we're about to vote, we can go back from this depth point and ask its pixel, tell us where you think the center of the 2D object you belong to lies. And we're going to take 3 different cues from this. We're going to take a geometric cue, a semantic cue, and a texture cue. Semantic cue and texture cue are easy to explain, right? The semantic is just, the 2D object detector already tells us this is a table. Could be useful information. So we're going to use that to enrich our vote features before voting. Same for the texture cues, right? We can look at around the pixel and say, maybe there's some interesting colors here. I'm simplifying things a little bit, but this is a good way to imagine this. And lastly, there's a very interesting geometric cue, which actually is very, very strong. So I'm going to skip one slide and we'll go back to this one in just 1 second. What is the geometry that a 2D can give us? So consider the following situation, right? We have a point. This is what we're seeing here is an object in 3D, and the image plane is depicted here. And what we are interested in is the center of the 3D object, which is point C here. But what we have is the pixel P, which is a point on the surface of the object, voting in the image plane to where the center in the image plane of the 2D object lies. So this roughly gives us the center of the 3D object, but only the direction. And in most cases, is also not too far from the actual location. So this is really useful, right? Because what we've done here is by using the 2D information, we can restrict the search space of the vote from anywhere in 3D to just along the line, the 1D line. So this is kind of reminding of what I said earlier about the Frostrum point network, if you remember, the Frostrum network that first detected 2D objects and then created a Frostrum. This is kind of similar, only this time, we're not making any decisions early on in the process. We're just helping the 3D vote by guiding it. We're telling it, this is where you need to be looking, right? This is the C prime here. And we're also going to give you the direction along which to search. So this is the geometric features that I'm talking about here. So we have geometric cues, semantic cues, and texture cues. All of them are going to be attached to the VoteNet features, these blue features here. So now we have 3 types of features. The blue ones are VoteNet features. The yellow ones are the image features. And these are just in gray, these are just the points. And the rest follows the same way VoteNet did before with the virtual point creation and aggregation and everything. I'm just hiding in this box here because I just presented this. There's a very interesting bit here about how to jointly train multimodal things like images and point clouds. I don't have time to go into the details. I just want to share that what was very useful here, and I'm citing the relevant paper, what was very useful here is to actually, at train time, train for every modality separately. And what do I mean by that? So imagine that we take the input point cloud, and in this case, here on the top, we're hiding the 3D point cloud features from the decision making, but we're still asking it to detect 3D objects. And we're doing the same here on the bottom. We're hiding the image features. And this forces the network to make useful predictions by not knowing anything about 3D and by not knowing anything about 2D. And of course, here in the center is using everything. This creates a much nicer training, which is more balanced between the different modalities. And at inference time, we're throwing away those 2 branches. We're just using the central one. If you want more details, look at the paper I'm citing. In terms of results, I want to highlight a few things. So first of all, this is VoteNet. The line here is VoteNet. It was, remember from before, it's the only work that didn't use RGB cues, but was still able to outperform. Here, I want to highlight one thing. If you're just simply adding RGB to every point, so now you have XYZ RGB, you're actually going to hurt performance. And this is not just evidenced by us. This is not a bug. This is a real result. You need to do something smarter. And here, hopefully, we were able to do that in iVoteNet and to improve the results by quite a bit. I want to maybe visualize this will be more insightful. So here's an interesting example. Remember when I mentioned earlier that 3D can have blind regions? So look at this black L-shaped sofa here. This was, if you look at the point cloud, there's just a hole, right? It seems like the sensor maybe was reflected and nothing was returned back to the sensor. So it's basically just a huge hole. There's, without the image, really, there's no way VoteNet was able to retrieve it. And indeed, it failed. But using iVoteNet, using the image, we were able to retrieve that back. Great. I think I want to leave some time for questions. I think I have, I don't know. Let me actually, Sivan, how long should I take further? I think I can wrap up in either 5 or 10 minutes. Which one is better? Depending on whether I delve into one. 10 minutes is also okay?
Should be okay.
All right, cool. That's great. Okay, so the main question I want to ask, now that I've introduced some scene understanding and point cloud processing, is, does this scale? I think looking forward, all I've shown you so far is using full supervision. So I knew everything by annotators. I knew the bounding boxes, I knew everything. I think if we seriously want to go forward with this direction, we need to start thinking of how to reduce supervision. For this, I imagine there are three important pillars that need to be explored, and this is my research directions in the past in the past few years, and this is where I'm going with this line of research. So first pillar is, yes, we need better scene understanding technologies. Even if they use full supervision, we need to improve the technology along that line. Another line another important pillar is what I mostly skipped in this talk is the processing of the point clouds themselves, right? We need to improve technologies for handling this unique type of data. This is much less mature than our case in 2D. And because I got some more minutes from Sivan, I'm going to actually use this opportunity and tell you a little bit about what we've done along these lines recently. I'm going to be quick, but yeah, we can always follow up later with some interesting questions. And then I'll tell you about the third pillar and where this is going. So this is a recent work where we try to explore, I was telling you that unordered points are interesting because here's the main reason, right? So imagine that your input set is a bunch of coordinates. Here, this is in M dimensions, but if this is a 3-point cloud, then this is just x1, x2, and x3, or xyz, however you want to call it. But the interesting bit here is that we want technologies that are invariant or equivariant to the order. Recently, and the papers I mentioned earlier, Pointnet, Pointnet++, and deep sets, this is exactly the type of questions they're dealing with. They're trying to say, what is the most general function we can create in a neural network that could process this type of data? Maybe it's important to say here, what is the alternative, right? Let's say that I just give you a fully connected network and I ask you to do processing of point clouds with it. How do you inform the network that even if I shuffle around the points, you still want the same output? You could just do augmentation, right? You could just permute in whatever way you want. But imagine the complexity of this thing. This is going to explode very quickly. So this is why we need proper techniques to do that. And yeah, and in this work I'm telling you here about is we try to go one step further and say sometimes the objects in the set are more complex than just points. Points are very simple structured, but it could be that the objects in our set, in our input set, are themselves complex objects with symmetries, like images, which has shift invariance property or shift symmetry, translation symmetry. So because I'm throwing around these terms, invariance and equivariance, let me kind of properly explain what I mean by that. Well, a function is called invariant if we apply the transformation and we expect the output to remain the same. To set an example, here's an image of a cat. Here's also an image of a cat. We want our function to be able to say that this is a cat, even though those images are not the same. That image is a translation of the object from this one. Still, we want our function to be invariant to that symmetry, to the translation symmetry. And equivariant is a small but important difference. We actually want, again, going back to the shift symmetry, if we shift around the object in the scene, we want our output prediction to shift in the same way. A good example is edge detection. If we have an edge detector that we can run on this image, we want it to produce edges. Now, it shouldn't matter whether we first shifted the objects and then ran our edge detector, or first ran our edge detector and then did the shifting. So this is the difference between invariance and equivariance. Now, in this work I'm telling you about, basically what we're saying is we want to respect the two types of symmetries. We want to respect the order invariance of the function, but also each of the objects, x1, x2 here, they also have their own symmetry group. If it's an image, then it's translation. If it's a point cloud, then again, this is an order invariance. So we can think of sets of sets. And We have some interesting theorem in this paper that basically says what is the most general linear layer that you could construct for this, and that respects both symmetries. And actually, the cool thing about this is a very simple way to go about this. Basically, what you need is to take a layer that respects the symmetry of the individual object, but instead of processing it independently, you also want to do this another type of that same layer with different learned parameters that process the summation of these elements. Here's an example from images. So imagine that you want to process a sequence. It's not a sequence, it's a set. The order doesn't matter. Maybe I took a few pictures of my car and they're blurry and I want to choose the best one, or I want to use them together and get a sharp image, right? So this is a case where I don't actually care about the order of in which I got the input. So this is why it's a set. And each element of the set is an image, therefore has interesting symmetries. So we already know that convnets or convolutional layer respect the shift equivariance property, sorry. But what I'm saying here is that you just need to add one small difference. You also want to process the sum of all these inputs, using another learned layer. And once you're done, you're going to sum those up back again. So a very small modification, but guarantees to get better results. This is why it's so cool. Going back to the context of 3D point clouds, as I said, sets of sets, right? So here is, for example, a set of point cloud of a person does some interesting motion and it's shuffled. And I'm asking the algorithm, tell me what is the center motion? Where is the center of the motion after it's been shuffled? And here you can see what happens if you just use point cloud processing. There's a lot going on between the different motions. And if you're not doing early fusion like I'm proposing here, you're actually going to lose a lot of performance here. This is the percentage of cases in which we were able to retrieve the correct image. Sorry, the first is images. This is point clouds and this is graphs. So we plot this both to meshes and point clouds. And you can see that the many variations of what we call our layer is a DSS, the many variations were working much better than not adding this layer. So this is something that is really cool. Okay, I'm closing the parenthesis and I also need to wrap up. The third pillar I wanted to mention is reducing supervision. I've been toying with some interesting problems in 2D, but now it's time to take all those three pillars and introduce this concept of reducing supervision for 3D scene understanding. I don't have time to tell you too much about these works, just throwing some teasers. If you're curious about talking about them afterwards, I'm happy to do it. But point contrast is a recent work where we, for the first time, try to take the very widely used transfer learning concept that's been widely used by probably for the last 5 or 7 years in 2D, but was never used properly in 3D. And we were asking a very fundamental question, like, how do we do transfer learning in 3D? What is the 3D counterpart of ImageNet to do pre-training on? And what is the algorithm, the technique that we need to do the pre-processing so that we could do fine-tuning on a downstream task and get good performance? And the bottom line here is we should totally be using pre-training. We propose some unsupervised pre-training technique based on the recently introduced contrastive learning. And we show across 6 different benchmarks, we always get improved results if we do proper pre-training. So this is very exciting. Another recent submission is trying to do semi-supervised. So this is where we have only a portion of our data that's labeled, but most of it is actually unlabeled. And we're able to properly contribute from the labeled part. We can pass forward pseudo labels to the unlabeled part. And those pseudo labels, if you're careful about the way you do them, you can actually squeeze a lot. But this is, you know VoteNet already, because I kind of told you about that for the past hour. So here, if we take VoteNet with only 10% of the data, we get a huge reduction in performance. But we were able to actually double that if we use the semi-supervised technique. Finally, this is a work about flow estimation. Scene flow is where you want to assign a motion vector for every point in the scene. This is a very common requirement in driving scenarios. The supervision here is crazy expensive. It's not just asking annotators to tell every point what its semantic class, but actually where the motion vector of that point is. This is not something you could ask. And it seems like fully supervised methods exist, but I don't think they're really scalable. And completely unsupervised methods exist, but they don't do well. And here we are in the middle, offering to use some weak supervision in the form of self-motion. and background foreground segmentation. And we were able to actually surpass even the performance of the fully supervised techniques by reducing the inaccuracy of the final prediction by more than 30 centimeters. So this is something really exciting. So hopefully we'll see published later on this year. Yeah, with this, I'm gonna end, and I'm almost out of time. Thank you so much for listening. If you care about 3D deep learning and you wanna kind of see what's going on recently, I'm one of the admins of this nice Twitter channel, which we call the TLDR of 3D deep learning. We have like over 1,300 followers, so this is a good place to catch up. And I'll maybe have time for a few questions now. I don't know. Sorry for stealing more time.
So if people want to ask questions, let's hear the questions.
I have a question. So
Please.
You spoke about combining the point clouds and the 2D, the images. Does that help? And you mentioned that inference you use both, but if at inference you can only use point clouds, does it help to train with the images?
It's a great question. I don't know. I need to try.
Okay.
I think it's a very simple thing to try, but I think it's a great idea. I should just do that and let you know.
Thanks.
Okay, anybody else? So I had a small question. Even going back to the 2D cow example, supposedly the patch needed first to do classification to decide that it's a patch of a cow, or maybe it's a cow and then the vector is one vector to the center. But if it's also similar to a patch of a chair, then the vector would point some other way. And in VoteNet, I didn't see that part anywhere.
Right, right. So I think you're kind of hitting the nail in the head. And one thing about this half voting is the whole framework I've shown on the cow kind of decides early on in the process, I'm interested, this is my cow detector. I'm not thinking of any other objects. We had to find a natural way to make this into an object detector that's already scalable, that's also scalable. Maybe, even between the two benchmarks I presented, there was difference in the number of output classes. So one network was trained to do just 10 classes, another one was trained on 18 or something. The way this is done is we're hoping that, again, the voting is done using aggregating some local features. So already in this stage, and it's not, maybe my hands are misleading, because when I'm saying aggregating local features, actually the receptive field we have at this point is roughly in the order of maybe like 1.5 meters or something. So that point already knows quite a bit about where it belongs to, and is pretty confident about what I think at this point, I believe it knows more than just the centroid. It kind of thinks it knows more about what type of objects it's voting for, and therefore it can carry along with its features something that later we're using. Let me just show you where exactly this is done. Yeah, so here, at the last moment, where the last part, we're telling all the points that kind of are in similar spatial or in spatial proximity, we're asking them together to decide on the class. But this feature is the same one that was carried all the way from the seed points. So hopefully it captures some information about the type of object it belongs to. Now, following exactly your idea, we had this hypothesis that maybe early on, we want to allow more votes. Maybe a point could say, well, I don't know, maybe I'm on the back of a chair, or I'm on the armrest of a sofa. And if it's the first case, I want to vote here. If it's the second case, I actually want to vote there. So we do allow points to vote, I think 3 times, if I remember correctly. I need to check the code, but I think it's 3 times. But it doesn't really change performance. So even if we don't allow them to vote more, it didn't change performance. I think the main reason is indoor scenes and the number of points we have sampled on the scene is quite large. So it's already enough. It's a good enough prior to make the vote pretty well informed. I think if we were to test this on outdoor scenes and we'd see a pedestrian that was sampled by, let's say, 10 or 15 points, the voting stage would be much more confused. And maybe there we'll see some advantage to using more votes than just one.
Okay, thanks. there is any other question from the audience, we can take it.
I have a question if no one else goes.
Yeah, go ahead.
So yeah, you mentioned the receptive field. So in like convolutional architectures for detection, a receptive field would see, it seems like it would see a larger part of the image. And here your seeds have, you said, relatively small receptive field. So the integration of sort of the larger picture, where does that happen? In the votes or?
Right. So after the votes, what we've actually done is, let's say, as you say, we had like 1 point on one part of the object, it knows something about its surrounding, and another point and another part of the object knows something about its own surroundings. Because they were voting to similar locations, in the next stage, in the red point cloud, the virtual point cloud, they're going to lie next to each other. At this point, we're again pushing them to another point cloud network. So at this point, they're already in spatial proximity, so they get to talk to each other.
But they don't talk to each other about the structure, right? There's no sort of integration of structure. They just
Well,
end up because they voted for
there isn't, right? Because I don't really know what's in those high dimensional features. I only know that I ask those high dimensional features to tell me what is the final semantic class and bounding boxes. So I can only hope that, you know, the way it can answer those questions is by carrying those useful information. And actually wanna you know, expand on this a little bit and say that we also tried to not, okay, so the integration between those red points could be done in many ways. One would be to say, let's just average the features of all the points that decided to go to the same place, right? And we tried that. We tried averaging them. We tried averaging them using some weighted RBF kernels. So, you know, you kind of downweight the further you are from the centroid. We tried a bunch of techniques. This is, we highlight this in the paper, but filtering them using another small network, another small MLP, actually gives huge boost in performance. And I think this filtering stage is crucial. Some points get there, and those points originated from non-objects, from the floor or from some other object. And the only way to get rid of them, or the only useful way to get rid of them, is using a nonlinear neural network. That's at least what evident, you know, the experiments show us.
Okay. So I think many of us are meeting you in the next few days, so I think we can wrap it up now. Thank you very much, Or, and thank you for everybody who participated. Good evening or good morning in California.
Thank you.
Okay, bye-bye. Thank you very much.
Bye-bye.